Okay, this is the handwritten example of an aggregate supply curve and an ISO equating supply and demand. So let's suppose there's an ISO, a system operator, that receives the following offers. They have a wind farm that is willing to produce 500 megawatt hours at $0 per megawatt hour. That's this first line here. They have a nuclear plant that's willing to produce 1,000 megawatt hours at $20 per megawatt hour. They have a coal plant that's willing to produce 2,000 megawatt hours at $50 per megawatt hour. A natural gas plant that's willing to produce 2,000 megawatt hours at $60 per megawatt hour. And then a fuel oil plant, in other words, they're basically burning diesel, um, at that's willing to produce 1,000 megawatt hours at $120 per megawatt hour. So let's draw this system supply curve. So 500 megawatt hours at $0 per megawatt hour. So we can draw that on here. So the x-axis here is going to be megawatt hours in thousands. So let's go to 500 megawatt hours at $0 per megawatt hour. That's going to be our wind. Then nuclear is 1,000 at $20 per megawatt hour. So we'll bump up to $20 and we'll add on 1,000. That's our nuclear. Our coal plant is 2,000 at $50 per megawatt hour. So 2,000 at $50, so that's going to be about here. And we'll add on an additional 2,000. So 1,000, 2,000. So this is coal, nuke, wind. Those are their capacities. Natural gas is 2,000 megawatt hours at $60 per megawatt hour, so we're going to jump up to $60 and add on another 2,000, 1,000, 2,000. So this is our natural gas. And then we have a fuel oil plant which is willing to produce 1,000 megawatt hours at 120. So we have to jump all the way up to 120 to get our last 1,000. Okay, great. So that's oil. So this is what we would call a merit curve, or an aggregate supply function. So it's who's going to be dispatched, who's willing to supply at the lowest price. So this is our aggregate supply function for this particular market. Now let's suppose electricity demand at 6 a.m. is 3,000 megawatt hours. What is the equilibrium price at 6 a.m. and which plants will run and how much will they generate? So let's say 3,000 megawatt hours is our demand at 6 a.m. So let's add that on here. At 3,000 we have a demand curve that's going to go like that. Remember, demand is always perfectly inelastic. Put that over there for now. What's our equilibrium price? Well, where does that demand curve intersect the aggregate supply function? It intersects it in the middle of the coal supply. So the equilibrium price at 6 a.m. is going to be $50. Let's make sure we had that right. Yep, coal is supplying at $50. So the equilibrium price at 6 a.m. is $50 per megawatt hour. Who's going to be dispatched, or who is going to produce or generate? It's going to be the coal. This much of the coal capacity. The stuff to the right, the stuff over here, that is not going to be dispatched because it's not needed. Aggregate demand ends at 3,000. So only about 80% of the coal capacity is going to be used at 6 a.m. All of the nuclear capacity is going to be used, and all of the wind capacity will be used. Who's not going to produce? The rest of the coal capacity, what I already mentioned. Natural gas and oil are not going to produce either. What about at 1800 hours or 6 p.m.? Suppose demand at 1800 hours is 6,000 megawatts. What is the price and what plants will produce? So let's put our aggregate demand curve here at 6 p.m. or 1800. What's our equilibrium price? Well, it's going to be the intersection of the aggregate supply function and the demand curve. So it's going to be $120 per megawatt hour. So you can see the price, the wholesale price jumped up, and it depends on what the aggregate demand is. And the aggregate demand during peak times like 6 p.m. is definitely going to be higher than the middle of the night or early morning like 6 a.m. So we see an outward shift in the demand function from early morning hours to the peak hours, and that's going to cause the wholesale price to go from $50 per megawatt all the way up to $120 per megawatt in the peak periods. So who's going to be dispatched? Well, it's everybody to the left of the demand function here. So we have a little bit of the oil capacity. This part's the part that I just highlighted there. This is going to be dispatched, but everything to the right, which I'm crossing out here, is not going to be dispatched. That's not going to be used. So about 50% of the oil capacity is going to be used. All the natural gas capacity is going to be used. All of the coal capacity at this point is going to be used. All the nuclear capacity and all the wind capacity is going to be used and dispatched. Here's a question. How will the wind farms earn any revenue in this market given their offer price of $0 per megawatt hour? Does it make sense for them to offer to produce all of their capacity at $0 per megawatt hour? Okay, so if you're a company, we've learned in probably micro that you want to charge your marginal cost. Well, the marginal cost for wind is essentially zero because the input cost, wind, the input prices, the price of wind is essentially zero. So they are essentially charging their marginal cost when they're willing to supply at $0 per megawatt hour. But the point here is that what they're receiving in this market is not $0 per megawatt hour. At 6 a.m., they're receiving $50 per megawatt hour because that was the equilibrium price in the market. And at 6 p.m., 1800 hours, they're receiving $120 per megawatt hour. So what is their incentive to offer to supply at $0 per megawatt hour? Well, it's that they're undercutting every other producer in this market all the time. They're always undercutting nuclear. They're always undercutting coal. They're always undercutting natural gas. There's no reason for them to supply or to offer to supply at any higher price because they're always going to be dispatched at some higher price than $0 per megawatt hour, unless it just so happens that demand is below 500 megawatts, which is essentially impossible in this market, right? So if demand happened to be here or something, there's no way, then they would receive $0 per megawatt hour, but there's really no way that's ever going to happen. So as long as demand is above 500 megawatts, they're going to make some money, and they're going to be dispatched, right? So if wind decided they were going to supply at $30 per megawatt hour, and it just so happened that demand was less than 1,000 megawatt hours, then all of nuclear would be supplied, but because nuclear is supplying at $20 per megawatt hour, but wind would not be dispatched. So it makes no sense for them to supply at anything higher than $0 per megawatt hour because that's their essentially their marginal cost, and so they're always going to be dispatched.